Okay, let's get started on this solutions video here. So here's our cane toad population starting out at 50,000 and growing to 88,000 in 6 months. That's the description there. We need to find the average monthly rate of growth. So we'll set up our equation here. All right, there's our exponential equation. 50,000 times e to the 6 times r for 6 months. The t equals 6 here. And the result of that is 88,000. Well, all I have to do is divide both sides by 50,000 first, so that gives me 1.76 over here. So it's e to the 6r equals 1.76. I take the natural log of both sides, and I'm going to move that 6r down and then divide by 6. I hope you're okay with that process and me going through that. But anyway, we get this natural log of 1.76 over 6, which gives me this decimal number here approximately, which gives us about 9.42% growth rate for those happy little toads. Actually, they're pretty big toads. But anyway, moving on to the next question. This is a log equation. I'm going to unwrap that by using the snail trail, so to speak. So 2 to the 4th equals x minus 5. Very quickly, you get x equals 21. The next one's a little bit different because we have log on both sides of the equation. And just think about this for a second. If you have the log of this equals the log of something else, both logs have the same base e. So basically, those arguments have to be equal to each other. That's just kind of hopefully a logical thing to say. So I'm just writing an equation with the arguments now because it's the log of both of them. And it's a quadratic equation. I'll set it equal to 0, as you always should. And 10x minus 5x squared, when you factor that side, giving you 5x times 2 minus x. So I'm just factoring the expression. It's both factors set equal to 0 means x equals 0 from this factor, and x equals 2 from this factor. Now, I have the 0 crossed out because earlier in class today we discussed that you cannot take the log of a number less than, the argument for a log expression has to be positive. It cannot be 0 or less than 0. So we have to discard this solution, x equals 0, can't equal 0, and our only solution left is x equals 2. Okay, moving on to expanding this crazy looking log expression here. We've got a product on the top, and we have a little thing on the bottom. We have a fraction, we have a quotient, log of a quotient, which means we've got to involve a subtraction of logs at some point. But we've got a product on the top, so that's going to be a sum of logs. Now, we kind of did it in 2 steps today in class. Natural log of 2x plus natural log of this 3/4 times x plus 1 here. I don't think I said that correct, but anyway, you see what I wrote down. On the bottom of the fraction is this square root, which I'm turning into an exponent of 1/2 and bringing it down in front of the logarithm. So minus 1/2 times natural log of x squared plus 4. But really, I should break up this natural log of 2x. That's natural log of 2 plus the natural log of x. And there's our complete breakdown of that log expression. Going backwards into the next problem, or I don't know if it's backwards or not, but anyway, go in the other direction. I'm going to first, just to simplify this little group of terms right here, that 1/2 is an exponent of 1/2 or square root. Natural log x minus natural log of 5 means natural log of x divided by 5. So there's that term. This one I'm bringing the exponent of 4 up, and this one I'm bringing the exponent of 1/3 up, but I'm rewriting it as a radical. You can leave it as an exponent. It's perfectly fine to do that. So a little bit of a simplification here in this step, and now I see I have sum of logs, which means log of a product. Difference of logs means log of a quotient, and I've got a single logarithm here now, and so I've got this root x over 5 times x minus 2 to the 4th power in the top of the fraction, and then cube root of x minus 1 in the bottom. The next problem is kind of a joke. You can rewrite that as baloney. All right, I'm not going to talk anymore about that. True, false. This statement is false. Logarithmic functions and exponential functions are not reciprocals. They are inverses of each other. Make sure that they are not the same thing. Reciprocals and inverses are not the same. The next statement is true. That's kind of an example of that, of a couple of log properties, the product rule and that power rule there too. The next one is false. This equation does not equal this equation here. Instead, this equation is equivalent to 2 to the 4th equals x plus 1. So that would be an appropriate correction statement for that falsehood. The next statement is true. That equation does equal this equation right here. So that was good. Flipping over the paper, the next statement, that equation is also true. That's a perfect example of the change of base rule for logarithms. The next one is false. It's kind of garbage. It's kind of hard to even make sense of either one of those things. That is not true. Natural log of x minus y cannot be simplified. That's one thing you could say. This statement is similar to this log property. Log of a quotient is equal to the difference of two logs. This statement is true. It looks a lot like that one in a way, but they're different. And so anyway, make sure you're clear on those log properties. The next three equations, I'm asking you to give both an exact answer and an approximation from your calculator. So when you take log base 10 of this side here and bring the exponent down, you get 2x plus 1 times the log of 10. Okay, so that log of 10 to the 2x plus 1 kind of comes down. Log of 10 equals 1. So it's just like natural log of e. This equals 1, therefore it's disappeared. On the right-hand side, you do have log of this number, 365.25. So to solve for x, the exact value is just achieved by subtracting 1 and then dividing by 2 in that order. So it's this expression here, log of 365.25 minus 1 over 2. When you let your calculator take over, then you get this approximation, 0.781. Next problem. The first thing I would do would be to divide both sides by 5,000. You want to isolate the the exponential expression before you take a log. So that equals 1/2. 2,500 over 5,000 is 0.5. So I'm going to take the natural log of both sides of this equation. I'm quickly jumping into this because the natural log of e is 1. All right, and we have this negative 0.77x, that's our exponent, equals natural log of 0.5. So natural log of 0.5 divided by negative 0.77 is our exact expression, okay, exact. And then that approximates 0.9002. Moving on, taking the natural log of both sides of that equation, I could use log log base 10, really doesn't matter. Gives me x equals natural log of 18 over natural log of 4, which is approximately 2.085. Okay, so that's how that one breaks down. The next one about Ben Schnusen. Yeah, he's been schnoozing. Actually, he's been in a coma for 5 years. Woke up, all good. We're going to use this equation here to figure out what interest rate his money was growing at because it was pretty amazing. He started out with $4,800, and after only 5 years, he had nearly $40,000. Whew. Anyway, here's our equation, 39,062.25. That's our amount. When we started with 4,800, we're using this A-port formula here, by the way. The rate we don't know, we're looking for that, and it's 5 years for t. So I'm going to first divide by the number, multiplying the exponential part of the equation, and then that gives me this value right here, 39 blah, 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 divided by 4,800 equals e to the 5r. I take the natural log of both sides. The natural log of e to the 5r kind of simplifies down to just 5r, and we get this number divided by 5, which is approximately 0.4229, or a holy moly 42.29% growth in Lucky Ben's money. Okay, hope that was good for you. Bye-bye.